Present now. Okay, and so this is very much making me realize how long the process of setting up for office hours is. All right, great. Okay, and we were at feature selection for today. Sorry, I think that's just down here. Which is really too bad because this is one of my favorite office hours sessions. Okay, there we go. All right, thanks for your patience. Again, my apologies. I will mention this a couple of times. I'm going to set up a remedial session on this, or a backup session, either, let's say, tomorrow or Friday. I'll poll the folks in the channel just to make sure that we can come up with the best time. I got thrown off my rhythm by the shuffle, and that's entirely on me. I should have logged it a lot better. Okay, feature selection. Feature selection is a superpower. I mean, it's just like the thing that more often than not will differentiate people or distinguish people who like really know their data science game from people who don't. And it's one of the biggest tells when you see somebody go from this like initial problem setting straight to a solution, straight to a model, and there's like no feature selection. Very often the problems that you get look like they're higher dimensional than they really are. So you'll have like a data set with like 30 different columns, and you're like, okay, I gotta throw those into my algorithm. Often people will actually like correctly scale their features and do all kinds of transformations, but they forget to actually select them. And there are a whole bunch of reasons why feature selection is really important. And I just realized this is the first real slide, which kind of makes sense. I want to start by talking about why the strategy is important in the first place. There's a fallacy, which is very common, which is to believe that the more features I have, like the more information my model has to work with. But I want to give you an analogy here to the way human beings learn. And this actually maps onto the way that machine learning models work as well. That'll hopefully help to explain why feature selection is important. So when you look at, imagine kindergartners, you're teaching a class of kindergartners. The amount of focus that you have to bring to bear to get them to focus on a really, really small, simple problem is huge, right? They're working with blocks and shapes and stuff, just kind of putting them together, very, very low level of abstraction. If you were to throw at a kindergartner a problem in engineering, they would be totally unable to deal with it. The problem is just way too high dimensional. They haven't had the practice at fitting all the different pieces together. So what they often have to do is start with a very simple, isolated problem with a limited feature set. They can deploy their knowledge to solve that problem and kind of understand it. And only once that problem is solved can you then maybe start to look at adding more features and enriching their view of the world. And machine learning algorithms kind of work the same way. If you give a random forest, for example, a suite of like 30 different features and you start to train it, it kind of has to learn the relationships between all the different variables, how they interact together, not just pairs, but even triplets and quadruplets of these variables, all those complex interactions. And while there is information often in those higher level terms, there really can be, it's often the case that that information is just more distracting than it is useful to the algorithm, especially early on during training. So when you have a limited amount of data that you can actually feed the algorithm, it is best usually to reduce your feature set because you want it to just learn the important things. You want it to focus on just the most important things because you want to squeeze those juices out from that limited data you have. The more data you get, the more you can start to say, okay, I can trust that my algorithm is going to learn, the most important feature relationships. It'll probably take it longer to reach the same level of performance than an equivalent algorithm trained on less data with a smaller feature set. But in the long run, it will reach a higher performance level. That's usually how these things play out. So you've got this kind of delicate balance between wanting your algorithm to learn the important things fast and wanting your algorithm to learn all the kind of nuances of your data. It's very easy to fall into the nuance trap, to think of machine learning as this single well-defined objective, like my machine learning model is either correct or it's not. And if you're thinking that way, you'll think of a model that doesn't get all the nuances right as being an incorrect model. Well, it's true that all models are wrong and some are useful. Your goal is really just to max out performance given a limited amount of data. And that's really where feature selection shines. That's where it becomes really critical to factor in. So yeah, essentially this is just kind of an initial motivation. There's some specific reasons that have names to them that I just want to list as well. Overfitting is one big one. These are all related, by the way, to that picture that I hopefully just put in your head. So overfitting is it's something that happens really easily, right? When you have a huge feature set, oftentimes there are relationships that essentially are mirages. You have so many different columns that just by chance, two of those columns might end up looking related when in reality they're not. As an example of this happens especially when you have small data sizes and not much data. So for example, imagine that you only had like 10 data points, right? But you had 100 different columns. The odds that two of those columns by pure chance will appear to be correlated are quite high, right? And that's really where overfitting comes in. You learn these spurious relationships, these mirages, these correlations that aren't actually real. And your algorithm can end up overfitting them. So this is one clear reason why you just want to cut down your feature list just for that purpose alone. The other one's compute cost. I mean, pretty common to see models that take a long time to train, especially these days. But even if you're looking at a fairly run-of-the-mill mundane application, less than a gigabyte of data, this could be a factor when you're getting to hyperparameter tuning or anyway, any number of operations like PCA or TSNE that do take a little bit more time, or certainly clustering, like hierarchical clustering. These things that don't scale super well, they don't scale as n, maybe it's like n log n or n squared. Those kinds of operations, it can make sense to cut down your features because it really tends to scale a lot better with a smaller feature set. One advantage so these are kind of like the downsides of I guess not doing feature selection. The positive side, I'm not even sure if these colors make sense, but anyway, think about interpretation as well as another value add. So the more features you have, the more homework you have to do to understand your problem deeply, right? If you decide to use 100 features, then you should probably do research on 100 features, unless you have a very compelling reason to think that your algorithm is just going to kind of figure out everything in a way that's reliable. That's often not the case, though. So this is worth thinking about. If you're doing a machine learning problem, you've got just 10 features to look at, you can probably become an expert on 10 things. That's not prohibitive. Once you get up to 20, okay, maybe, but 50 and above, really you have to start asking yourself, there's that time expertise trade-off, and you're going to have to come down somewhere on that calculation. Wherever you come down, it's probably not with the full feature set, so feature selection is something you want to think about. Somebody just dropped a comment. So Jeremy says, is feature selection still important in neural nets? Oh, yeah, this is a great question. Given their structure or this process mostly for non-deep learning models? Excellent question. So it's something that we're often told about neural networks, that they kind of do feature engineering for us. We're often told it's this black box and you can feed in anything you want. And let's say that you have features 1 and 2. And it turns out that feature 1 and feature 2 don't really tell you much, but when you do, some operation like feature 1 divided by feature 2, all of a sudden that's a really informative feature. And what we're often told is don't worry about doing that feature engineering up front with a neural network. The network will just kind of learn that feature 1 over feature 2 is the important thing. And that's true in the limit of infinite data. A lot of things are true in the limit of infinite data. One of them is that neural networks, a fully connected dense net, if you're familiar with neural networks, if not, then feel free to kind of zone out for this part of the conversation, but a fully connected neural network, in principle, with infinite data can solve any problem. It can be an artificial general intelligence with sufficient amounts of data and sufficient size and so on. But the reality is we have a limited amount. The more that you require your model to learn about the problem, the more you throw at it, the more noise you throw at it, the more data it's going to have to chew through to kind of realize, oh shit, this is connected to that, and that's connected to that. This is a lot like the way humans learn, right? If you started somebody off in medical school training or something by throwing them into a hospital without letting them see any textbooks, they'd just be shaken. They'd look around I have no idea how to start. People are throwing charts at them. They're doing other medical things that I don't know about. The bottom line is the feature set's just way too big. And if you gave them just one day to be trained in that way, you'd end up with a useless person, right? They wouldn't be able to do much. But if you gave them a full year of exposure to that setting, eventually they'd start to be oh, yeah, okay, this is connected to that and this is connected to that. And they might even learn more nuanced things than a doctor whose brain is kind of pre-feature selected. As they go through this training, they're taught to look at things from a certain perspective. These people who just get thrown into the situation might actually end up learning more interesting things. They might have insights that doctors wouldn't have picked up on because of the way they were trained. But in practice, you've got to restrict the feature set, because otherwise we're a lot more like the resident who gets thrown in with a day of experience or something. So your models, your deep learning models, are like that too. There's this trade-off of how much work do you want the model to do versus how much work are you going to do up front. And the more pruning you do, the more feature engineering, the more feature selection, the less the model has to figure out, the further it will be able to go based on a finite data set size. So it's up to you to figure out, oh, I've got a big data set, therefore I can count on my model to learn these nuances, or I've got a smaller one and I can't. In practice, that choice, you actually don't make it in the way I just described. It's not like you look at your problem, you're like, oh, I have a lot of data, therefore I should do these things, right? It's not actually that obvious. What you end up doing is trial and error. You end up saying like, okay, my model's not performing great. Maybe one possibility is I'm asking it to learn too much. I'm asking too much of it. So maybe now I augment I give it a leg up by doing my own feature selection, feature engineering, or whatever. But it's a continuum. It's a push and pull. You're in a relationship now with your machine learning algorithm, whether it's a deep neural network or a random forest or whatever else. You've got to give a little, it's going to help you a little, and you're essentially exchanging cognitive forces, and you have to decide what that balance point is between the two of you. So hope that wasn't too abstract, but anyway. Okay, the last thing is improved accuracy, and this is, I almost included this like just to be contrarian, just to stir shit up here. But basically the idea is most people will go, oh no, like how can your accuracy possibly go up if you include more features? Again, same thing here, right? If you reduce the problem set down, or the scope of the problem down to a limited set of features that are really important with a limited amount of data, you will actually perform better than if you give this whole super complicated problem that the algorithm has to figure out all these complicated relationships. It can't tell that like feature 1 is more important than feature 2 out the gate. It has to learn that, and it has to learn that slowly. So there's this like extra piece of homework that you're asking your model to do before you even get into like the fine tuning of things, just to figure out, hey, what are the features you should start by focusing on? And that extra step, that's going to cost you accuracy, because that's you eating through a whole chunk of your data set just to get to the point where your model realizes where it should be focusing to start. So there's a lot of anthropomorphizing that I'm doing of machine learning models in this. I'm doing it to give you kind of an intuition for how this works. It's not meant to be quite literal, but it's also hopefully somewhat directionally right. So anyway, just some ideas to chew on there. Maybe I'll stop with this setting right now and check in to see if there are any questions before I dive into the actual techniques. Does anybody want to ask anything at this stage? Okay, cool.
I have a question brewing that it's not totally formed, but I'm going to sort of pitch it out here since we're in question
Go for
mode. So, my go-to whenever I just want to quickly build some sort of base model is throw it into a random forest.
Right.
One of my favorite things about that is that you can export feature importance out of that random forest model. But I'm curious, once you get into the world of deep learning especially, does that feature importance still translate over from kind of that non-deep learning model over to what a neural net might find instead?
This isn't a half-baked question. This is like, I would say, the philosophical core of what we will hopefully explore this office hour. So that's a really deep question, and the answer to it depends on how exactly you're calculating feature importances with your random forest, or at least it partially depends on that. And it also depends on a couple of other things that we'll discuss. But it is an excellent question. You should hold on to it and hold me to account if I don't end up addressing it by the end. Is that okay?
You got it.
Okay, perfect. So that, by the way, I mean, everybody can kind of keep that brewing in the back of your mind. Hopefully it'll all be revealed in due course. Let's start with some naive strategies here, feature selection. So one that people, that basically everybody knows about, but that they don't give them credit for knowing is, or give themselves credit for knowing, is this idea of variance threshold feature selection. You all kind of implicitly know it when you see it. So here's an example of a data set that contains what seems to be a redundant column. right? We have height, weight, age, and athletic ability, supposing we could score that somehow. Notice this age column, like it is all 24s. There's like a 21 here, but I mean, sure, one person is 21 years old, but this column is really not adding a lot of information to our problem, right? We've got basically a redundant column. It might as well just be all like the letter A or something, and there's no value here. There's nothing we could learn from it. I mean, we're basically learning a whole bunch about what 24-year-olds are like, and then we've got one example of a 21-year-old, but basically this is a data set about 24-year-olds and their athletic abilities. So what this means is really age column is absolutely redundant, and we'd want to eliminate it. Now, we'd all probably come to this conclusion, at least if we spent enough time poking around at our data sets. But we might not come up with exactly the right articulation of what it is that we're doing, that our brains are doing when we come to this decision. And that articulation is actually captured in this term variance threshold feature selection. So what we're really doing, what our brains are doing, is we're looking at this column and we're saying, well, the variance is actually really low, right? All these values are basically the same. So the value of each of these ages is the same as the mean, basically, or very close to it. They're all basically have a variance of 0. Okay, so this gives us immediately our first way of just discarding a column. If the variance is low, kick it to the curb. This column is not useful. So one quick way to do it. By the way, this is called, sorry, I should put this in context. These techniques that I'm describing, of which variance threshold feature selection is an example, these are going to be called filter methods. The reason they're called filter methods, or actually, sorry, not the reason they're called that, but the special thing about them is that they're only going to look at the data set. So these are techniques we can use by just like being given a data set. You look at it and you're like, okay, just by inspecting this data set, I can throw this guy out and I can throw that guy out and so on. So that's what we mean when we say filter methods. You're just given a data set. You never train a model. There's no reference to random forests or logistic regressions, anything here. It's just the data set. So you can see why variance threshold feature selection is an example, right? Just look at the data set, age column, okay, the variance is below a certain threshold, cut it out. Scikit-learn gives you tools that allow you to do that too. Here's another one. So I don't even know if I have a name for this one. This is just like drop a column when it doesn't contain enough information, right? So age is like, we have 3 different values and like basically nothing anywhere else. Yeah, ditch it, right? So this is another example technically of this so-called filter method. You're just staring at your data set, looking at it, and you're like, okay, obviously that's a bad column. Let's scrap it. Okay, less maybe obvious initially is this idea of using a correlation matrix. So I'm going to just describe what a correlation matrix is in a little bit of detail to make sure we're absolutely 600% on the exact same page with respect to the meaning of this, because the details really matter here, as we'll see in a minute. Okay, a correlation coefficient, a Pearson correlation coefficient, an R-squared value. All these things are synonymous. They're all synonyms. This is a single number. Okay, the correlation coefficient is a single number that tells you how linearly correlated 2 variables are. Linearly correlated 2 variables are. So in other words, if I have arm span and height, and they're like clearly linearly correlated, there's like a straight line relationship between the two, my Pearson correlation coefficient will be 1. If they're not at all related and it's just this like, the distribution is just like a random cloud of points, then the correlation coefficient is 0. So 1 is super high correlation, 0 is no correlation, and then negative 1 would be a super high negative correlation. So if I increased my arm span and somehow my height went down, that would be a -1 or a negative Pearson correlation coefficient. Okay, now the key here is that linearity assumption, and a lot of people, including seasoned data scientists, forget about this one, and the implications of forgetting about it are sometimes quite important. So suppose arm span and height were not linearly correlated, but they were instead correlated like exponentially, right? There's a bit of a curve to it. You're still probably going to get a positive Pearson correlation coefficient, and in practice, if the exponential correlation is really high, if it's pretty clean exponential, it's probably going to be pretty close to 1, like 0.8 or 0.7, something like that. But it's not going to be 1, and the key is it's not going to be 1 to the extent that that curve deviates from linearity. And moreover, there are relationships between variables that are really important, but that do not look linear at all and can in fact fool a Pearson correlation coefficient into not just being not 1, but being outright 0. And an example of this would be a case where you have an optimum. So let's say that our x-axis is, what did I say? Like, let's say arm span, and our y-axis is height. And let's say that, okay, let's pick something maybe more intuitive. Let's pick weight as the x-axis and then athletic ability as the y. Okay, so you've got, for different weights, how athletic are you? Well, if you're super skinny, maybe you're not super great at whatever sport we're talking about, right? Like sumo wrestling or something like that, right? So early on, like at low weights, you do very poorly. But then as your weight goes up, you do better and better until there's an optimum. And then eventually you're just like, you're too overweight, you don't have the cardio or whatever, and you're not able to perform well. So there's an optimum weight for this particular sport, for this athletic ability. In that case, you'd expect your points to pretty much follow a curve like that. Hopefully you can see my hand gesture. And if you try to fit a straight line to that, like that's actually the Pearson correlation coefficient you're going to get is going to seem kind of random because it's not monotonic. And that really confuses the hell out of this linear assumption. So there are a lot of important relationships that can sometimes really be very deeply wrong when you try to capture them with Pearson correlation coefficients. So with that in mind, with that massive caveat, let's now talk about how you can use Pearson correlation to inform your feature selection. Okay, first thing, let's imagine you have two features that are so incredibly similar that they basically give you a one-to-one mapping. When you plot one against the other, they have an exact straight line relationship. Let's say arm span and height, because they're already pretty closely related. Let's say they're exactly related. In other words, if you tell me your arm span, I can tell exactly what your height's going to be. I just go to my plot, I look at where the line says it should be, and boom, that's exactly where you're going to be. All the points lie on that line. If that happens, then arm span and height are redundant features. They're telling you the same information. In other words, there's no reason for you to keep both. In fact, you're better off ditching one. So that's one way to decide to ditch a feature, is if the correlation coefficient, the linear correlation between those two features, is very close to 1. There's a continuum there. Like, the closer you are to that perfect straight line correlation, the more redundant those features are. Okay, so that's one aspect. But there's a second way that you can use Pearson correlation coefficients to decide which features to rip out. And it's also kind of crude because, again, it makes the assumption of linearity. It has to do with looking at the thing you're trying to predict. So let's say you have, in this case, a whole bunch of different, so we're imagining a car. So this is what all these features are: miles per gallon, cylinders, displacement, horsepower, weight, and acceleration. Let's say we're trying to predict acceleration, right? We're curious sports car buffs, and we want to make a model that tells us, like, how should you build a sports car to give the best acceleration possible, right? Okay, well, here are our inputs. We have 5 different things: MPG, cylinders, displacement, horsepower, and weight. If we're trying to decide whether or not to cut one of these out, one of these features, because we don't think it's useful, one way, very crudely, that we could decide which feature to kick out would be to just ask, hey, is that feature like correlated to acceleration? Like, is it obviously correlated? Is there a linear relationship between them or something like a linear relationship between them? If the answer is yes, if there's a really strong relationship, for example, between like miles per gallon and acceleration, then damn, I want miles per gallon in my model, right? Like, I don't want to lose that. That's a really valuable input. On the other hand, if something like, I don't know, weight or something has a really low, close to 0 correlation with acceleration, all of a sudden, like, what do I, maybe I lose something. It could be the case that weight alone doesn't correlate with acceleration, but when you combine it with other stuff, like, weight and horsepower, first, if your weight is below this, but your horsepower is above this, then that tells you the acceleration. That's always possible. But if you assume that you're not looking at interactions between features, this can be a decent first order pass, like kind of first approximation. And that's exactly what this technique is going to use. It's going to set a cutoff for the correlation coefficient between inputs, specific inputs, and the thing you're trying to predict. And if those correlation coefficients are too low, you kind of say, okay, this is going to sting a little bit, because again, there are a lot of assumptions about like linearity and variable interactions that I'm ignoring here. But yeah, let's say if I've got to ditch a feature, I'm going to choose to ditch that one because it's to first order, not directly correlated. Any questions about this piece? Because I know it's got a couple layers to it.
I have a question.
Yeah.
I recognize we're talking about like a first order pass that you would want to make, but without looking at any like real scatter plots for how something looks, especially if it has sort of that optimal kind of shape to it or some sort of like parametric structure to it instead, just throwing it out, even at this point, seems reckless.
Yeah. 100%. Okay, good, excellent. I'm glad you raised that. In fact, this makes me realize there's a missing slide here. One feature selection technique is like just look at the plots. Look at the actual scatter plots. Don't trust like correlation coefficients that make assumptions about linearity. Don't trust those to just be a silver bullet. The cases where you might actually want to use this are not cases where you have 5 inputs and you're looking to predict something. They're cases where you might have like 200 inputs, and you really do not have time to look at, especially when we talk about correlation, like redundancies between features. 200 by 200, you're looking at like whatever that is, 40,000. I don't know if it's, okay, crap. I think it's 40,000. You don't have time to look at 40,000, or I guess 40,000 divided by 2 because it's an upper triangular matrix. Doesn't really matter. You don't have time to look at 20,000 different features. So this is a blanket rule that kind of quickly gets you into a less dicey territory. But you're absolutely right. Like for many, many cases, just look at the friggin' plots. Yeah, don't worry about the correlation coefficients and so on. I'm flagging this really as just to complete your toolbox. This is a technique that gets used a lot, especially with very large, high-dimensional data sets. But again, your mileage may vary, and always look at the plots. I think, Jeremy, your point, to the extent that it directs our attention towards looking at plots, like that is never a bad thing. And in a case like this, you're totally right. Like I would be a lunatic to throw something out purely on the basis of like, the correlation coefficient, because I can afford to look at these 5 features, right? I have the time. So yeah, a really good point. Thanks for calling that out.
Yeah, sure.
Okay, any other questions before we slide along? Okay. All right, feel free to chime in at any point. I'm going to briefly touch on PCA here. I do an office hour on PCA, and I like to work it from the ground up because there are nuances that are easy to miss. So pretty much this is just a quick aside, especially if you know PCA already. We can talk about it here. So one thing that you could do is use PCA to reduce the dimensionality of your problem. That's not the same thing as selecting specific features, because what you're going to do is blend features together. But if you know what PCA is, basically you say, okay, I'm going to take the first 10 principal components and just use those to solve my problem. So you can use this. It is kind of equivalent to feature selection through a certain lens. I guess I more just want to draw your attention, if you're already familiar to this concept, I want to draw your attention to the fact that when you do that, you are actually kind of doing a combination of feature selection and feature engineering at the same time, because each principal component is an engineered blend of all the other features, the original features that you had in your feature set. So I guess just keep that in mind. This doesn't get done very often, for a whole bunch of reasons that have to do with interpretability, like your principal components. It's not super clear how to interpret them all the time, and it does serve to kind of blend things together in a way that's not always productive. But again, just flagging this conceptually, PCA could be viewed as a mechanism for feature selection. So if that doesn't make sense, you can discard it from your brain. If it does, great. I mean, hopefully it helps you understand PCA a little bit more deeply. Oh,
yeah, I have a question.
Yeah.
Yeah, I also tried PCA in one of my recent projects, and the accuracy went down. I'm not that familiar deeply about PCA, but I was wondering, are there like particular type of data set it is more useful than other, or?
Yeah, this is a great question. So it is never, as a rule, obvious what techniques you should use on a given data set. Like, or at least for I'm talking about tabular data here. If you get images, then yeah, you need to use like deep learning or if whatever. But if you're just given like a tabular data set and you have no reason to think that there's any particular structure in your data a priori, then yeah, I mean, it's a bit of a crapshoot. You kind of have to try different things. I will say, like, trying PCA as a feature selection strategy, I just wouldn't do that unless I had a strong reason to think that this was like a silver bullet for my problem for, I don't know, some external reason. I've never done this. I've never solved a data science problem using PCA in this way, and I don't know many people who have. Usually I would use a technique like this if the problem was really high dimensional. I certainly would use these sort of like variance threshold approaches, but the default one that I would use is actually one of the strategies that we're about to encounter. Yeah, so short answer is I think PCA tends to be a little too clever, let's say. It's too clever by half. It does too much of the pre-processing for you. PCA makes assumptions about linearity, so it can only capture linear trends in your data. So anything nonlinear gets lost. So in that sense, it's just as dangerous as this guy right here. It's just that it manifests in a different way. So a lot of reasons to generally I would say stay away from PCA by default.
Okay, thank you.
No problem. And again, that might become, I think, clear when we do a PCA office hour. Okay, so next, we've been talking, again, just as a quick reminder, this is all in the context of filter models. Okay, so we've just been looking at the data set, right? So that's all we need to do this. You can just look at a data set, drop a column, just look at a data set, notice that missing values are there, drop the column, just look at a data set and calculate the correlation coefficients, drop the column, or just look at a data set, calculate the PCA like vectors and drop the, etc. Okay. Now, what about the case where you've actually called model.fit, right? These are model-dependent strategies. So just to give you the brief story of how these work, you basically fit a model to your data set. That model will have learned things, we hope, about which features are important and which aren't. Certain models, by certain definitions, pay more attention to some features than others. And then the reasonable question is, okay, what are the features that my model is paying the most attention to, and can I retain those features while throwing out the rest, right? So this is really what model-dependent strategies is going to involve. And different models have different model-dependent strategies. This is where we start to get into the territory that Jeremy was gesturing at earlier when he said, like, wait a minute, can I really compare like the features that a random forest says are important to the ones that a neural network says are important? Like, is that really apples to apples? And, well, we'll see. This is going to be part of the answer to that question. So let's start with a decision tree. Again, we do decision tree, an office hour on decision trees. It's, I think, something that's very much worth diving into and understanding deeply, partly because it allows you to understand how feature importances are calculated for decision trees, but also just partly because decision trees and tree-based models more generally are ubiquitous, and I highly recommend using them as your default. But just to show you how these trees work, I'm not going to explain how they're formed, but I'll explain how they make predictions at test time. So we have essentially our, let's say we have a new sample. That's right. This is a data set of like hockey players. And we're trying to predict based on these players' heights and weights and the average time that their coaches put them on the ice during a game and their salaries and so on. We're trying to predict how many goals they're going to score in a season, I guess. So imagine taking a new player, you put them at the top of the decision tree, and at first we ask the question, okay, is this player's height less than 6.1 feet? And if the answer is true, they go into this bucket here. I'm just going to move my mouse around so that, well, sorry, usually on Macs the mouse becomes big when you do that. Doesn't look like it's happening, but anyway. Okay, so hopefully you can see my mouse. But so if the player is shorter than 6.1 feet, they end up here. And then it goes, okay, well, is your weight less than 182 pounds? They end up here. Okay. There's a sense in which the questions that this decision tree seems to ask the most often, or the features it seems to ask about the most often, might just be the more important features, right? Like if it was asking like, hey, are you shorter than 6'1"? Okay, in that case, are you shorter than 5'4"? Okay, in that case, are you shorter than 5'1", and so on. Like if you're asking about height an awful lot in order to make your prediction, that suggests that height is actually a really important parameter. And if that's the case, we should probably rank it high in our priorities and get rid of features that don't show up at all or very little in these structures. So that's going to be the core of the idea behind the bespoke feature importance metric that decision trees use, in particular in scikit-learn. So today, if you do, from scikit-learn regression or whatever, import random forest regressor, decision tree regressor, boy, anybody who's working on a project right now is going to feel embarrassed on my behalf. I messed up the import statement. Anyway, if you import a machine learning model, a tree-based model, this is what it's going to do when you do model.feature_importances_. And that command in scikit-learn is essentially just doing this. It's going through your tree, and it's saying, okay, height was asked about once, looks like just once, so cool, height gets asked about once. But we ask about height for all samples. Like all samples have to go through this top-level node. And so, in that sense, it's probably a disproportionately important question. It's the very first question your tree is asking. So yeah, height will be weighted pretty decently, even though it shows up only once. But then look, weight shows up 3 times we're asking about it, twice at the second level and once at the third level. So pretty important, pretty early, we're asking about these questions, or asking about this feature. And so weight is probably really important. I mean, average ice time shows up once down here and salary shows up once down there. So probably, again, less important things. And that's how the feature importance score is going to be calculated in scikit-learn for decision trees. So if you're ever wondering where this comes from, hopefully now you know it's from this process. However, if we look at a different algorithm, this you might recognize as essentially the basis for linear or logistic regression, right? So what we have is some parameter. So x is our feature, and w is the weight that we assign to that feature. Essentially, all linear or logistic regression do is they say, okay, I'm trying to calculate how good of a hockey player you're going to be, and I know your height, your weight, your ice time, and so on. What I'm going to do is I'm going to take those numbers, I'm going to take the height, and I'll multiply it by some number that I'll call a weight, which actually is pretty confusing because, okay, well, anyway, it's not weight, but you'll take the height, multiply it by some number, add it to the weight multiplied by some number, add it to the ice time multiplied by some number. So you add those all together. It's essentially, those numbers you're multiplying them by are the coefficients that determine how much of a say that feature gets in the overall sum. And then whatever that sum is, it determines what the prediction of the algorithm is going to be at the end of the day. And so the larger the weight of that particular parameter, the weight value that you multiply the feature by, the more important that feature must be, right? If you do height times 1,000,000 plus ice time times 10 and a bunch of other things with lower numbers, well, probably height is like really important, because if you just change the height a little bit, it gets multiplied by 1,000,000 and has a way disproportionate impact on the ultimate prediction of the system. And so that's your hint that height is really important. And you can see like the rationale here, right, is completely different from the decision tree. Both are sort of nice heuristics. They're kind of intuitive, and some guy like me can convince you that, yeah, they kind of generally make sense in the span of a couple minute explanation. But there's nothing consistent here. Like, to Jeremy's point, like the logic that you're using to determine which features are important when you look at logistic regression's weights, that's completely different logic from what you're using to determine which features are important in a decision tree. So that's one level on which these things are really not apples to apples. But it's not the only one, right? I cannot use the same feature importance strategy on decision trees as for logistic regression, but as a completely separate point, decision trees will tend to look for different things when they're being trained than logistic regression or linear regression. Linear regression, for example, is only capable of detecting linear correlations between features, right? That's the only kind of interaction it's able to capture. Every prediction you get from linear regression is just going to make assumptions about like features being linearly correlated. And that falls prey to, we talked earlier about the example of the sumo wrestler, right? Like if there's an optimal weight where the sumo wrestlers are really good at performing, that's going to seem like the relationship there is not going to seem linear, and logistic regression or linear regression will completely miss out on that feature. It will assign a very low weight to that feature, and you'll end up throwing it out when in reality it might be one of your best predictive features. Decision trees, on the other hand, won't make that mistake, which is exactly why decision trees are able to capture some nuance that logistic regression can't. And for that reason, the feature importances that you get from decision trees and logistic regression are different, not only because they're philosophically different, not only because they come from different mathematics, but also because they come from just a different lens on the data. The machine learning model literally is looking at the data in a different way. Here it's making an assumption about linearity, so it's going to come up with one set of feature importances that, it's only able to notice the features that have linear relationships. And here it's not making those assumptions, it's making a different set of assumptions that are a little bit more subtle and hard to get across. But the bottom line is they're not looking at the data the same way, and so they end up flagging different features as being important, in addition to sort of having different structures, different definitions of feature importance. So that's I think, important things to clarify is like, don't expect, for example, to use logistic regression to do feature importance and to calculate, to do feature selection and calculate your feature importances, and then use those features in a decision tree, right? That would be counterproductive. You're then trying to you make assumptions about linearity, you pick only the features that were linearly correlated and ditch some that, who knows, maybe the decision tree could have used better than the logistic regression. So something's lost in translation there. And that means you really always want to be, as much as possible, you want to be using a particular model to figure out feature importances for that particular model, and not for, mixing and matching, taking feature importance from model 1 and then using those to select features for later use in model 2. You really want to, train for the way the model is going to perform in the wild. Any questions about decision trees or logistic regression feature importance?
Guess who has another question?
Yeah, no, go for it. This is great. Someone has to.
So I understand why you can't necessarily do an apples-to-apples comparison for feature importance from a decision tree to a linear regression. But can you do more of an apples-to-apples comparison amongst any sort of tree-based model? Decision tree, random forest, XGBoost, etc.
Yeah, that's a great question. The short answer is yes. So I guess I was sort of subtly trying to avoid the question by suggesting this should just never be done. And part of me just kind of wants to say, yeah, just kind of don't do it and just use, if you're going to use a XGBoost or a decision tree, use XGBoost or a decision tree for both feature selection and prediction. But you are right. It is the case that, for example, linear logistic regression makes the assumption that your data is linear. It will be really, really good at sniping out linear correlations, and it will be really, really terrible at noticing nonlinear correlations. Now, this means there are other models that make assumptions about linearity too, right? There's support vector machines with a linear kernel. So if you end up using linear regression and you're like, oh, here's my feature importances, you'll probably, with some caveats, you'll probably end up finding that those features perform disproportionately well when you then feed them into a support vector machine with a linear kernel than they do if you feed them into a decision tree, something that makes completely different assumptions about linearity. So the same is true, as you rightly point out. If you use a tree-based model to do your feature importances, I can certainly see a theoretical argument why you would expect those features to translate better, because decision tree is going to be good at spotting a certain class of thing, and other models not. So yes, the short answer is you're absolutely right, though I would generally recommend doing exactly the same in training and feature selection. But that's a very good and subtle point. Yeah.
Cool. Thank you.
No problem. Yeah, Navjot.
Yeah, I have a question here. So I understand we cannot use the important feature from linear regression to decision tree, but Jeremy asked if we can compare important feature from one decision tree to the other tree-based model. But why do we have to do it? Because decision tree we use random forest and XGBoost to avoid overfitting, so that our model randomly pick the features. So why I have to take important feature from decision tree, which is overfitting, to feed my random, forest.
Okay, so this is another excellent question. And I'm going to try to give you a Frankenstein monster kind of concocted, contrived scenario that's going to try desperately to manufacture this into making sense. So hopefully this will work. Let's imagine a situation where we have an absolutely gigantic data set, and for whatever reason we insist on using that whole data set to do our feature selection right out the gate, right? If we feed that whole giant data set to a model, let's say a random forest with 1,000 estimators, we know it's going to take till Sunday to run, right? So we don't want to do that. So instead, what we say is, okay, why don't we just, I don't know, pick one decision tree and run this data through that decision tree. It'll be 1,000 times faster. We'll have the feature importances by this afternoon, and we'll be able to go home. So that would be the kind of contrived scenario where this would happen. In practice, I would say, whoa, maybe start by reducing the data set size. I think you're better off going with a random forest and a smaller data set than going with fewer estimators, like just using one decision tree, but using the whole data set. That's I think like the closest I can come to making that work. But if I understand Jeremy's point, it was sort of a more theoretical one. But you're right, Navjot, that it's worth thinking about like when you would actually in practice want to do that. Does that make sense?
Yeah, that makes sense. Thank you.
Okay, cool.
And if I can also just clarify what I had brought up a little bit, it was very much based in the idea of having a baseline model before you build out something more advanced. So in this scenario, for example, like if I want to have a baseline and a more advanced model that I can compare as apples to apples as possible, from what I am understanding here from this presentation, like let's say that my more advanced model is going to be an XGBoost model, I would be better served using a basic decision tree as a baseline than using a logistic regression as a baseline.
Yes. Excellent points. Yeah, that's great. I'm really glad that I started recording this because I think that there's going to be value here for people listening to this who want to explore these scenarios. These are all really good questions. Parsing out when and why you would use different things. Yeah. Now to add a little bit of color and hedging to that, what I might say is I suspect so setting the baseline is good. I would always recommend using a simple decision tree first to start to understand your problem. What I would not recommend doing is using that simple decision tree to come up with features that you want to select out. What I would actually recommend is to use XGBoost then, after you've gotten an understanding of your single decision tree and you're like, oh, okay, I kind of know what's going on here. It all makes sense. Throw XGBoost at it and use that for feature selection and then for your actual predictions down the road, just to maximize that matchup. Though again, I want to hedge. I mean, I can imagine there being scenarios where it makes sense to not quite go in that direction. So it's complicated. It's like a your mileage may vary type thing, but hopefully being aware of these different realities is at least enough of a guide for these things. So yeah, great points, guys. Okay, so, oh yeah, good. Okay, to close. Now it's time for the Mack Daddy solution, the one and only. Sorry, I'm overhyping this, but it's the one that I think everybody should use. It's very rare that you shouldn't use this one. Okay, I don't like this. I don't like the idea that my feature selection in logistic regression, my feature selection in decision trees, these are philosophically incompatible. And it just makes comparisons impossible and kind of irresponsible to a certain degree. So what if there was a way that we could do this in a model agnostic way? So what I mean by that is, what if we could come up with a metric that was philosophically consistent across, like you use the same technique to train or to do feature selection for a logistic regression as for a decision tree. And there is such an approach, and it's called permutation feature importance. And I just want to sketch it out here really quickly. So again, we're looking at our familiar data set of height, weight, age, athletic ability. I guess here I have that redundant age column. So, I mean, yeah, we probably would have just dropped that earlier. But anyway, Here's what we're going to do. We're going to train our model, and but before we train it, we're going to pick one of these columns, and we're just going to shuffle it. So we're going to take every value in that column and shuffle it. So move the value in row 1 to row 6 to row 2, row 2 to row 7, and so on. Shuffle the whole column. Essentially what we're doing is we're destroying the correlations between that column and all the others. So there's no longer like, this weight of 150 is no longer correlated to a height of 1.6 and an age of 24. Now it's moved over to somewhere else. Essentially, we've destroyed the information in this column, the predictive value of that information. It's also no longer correlated to the thing we're trying to predict, the athletic ability over here. And then we run our algorithm again, and we look at what is our predictive accuracy or whatever metric we want to measure. And presumably, if that feature was really important, what would you expect to see? You'd expect to see a big drop in the performance of the model, right? So you train it on the full feature set, and then you just like randomly shuffle one of the features, and then you try again, and you see, oh, look, my performance just dropped, like my accuracy dropped by 10%. Well, presumably, whatever feature it was that I just completely nuked by shuffling it, that must have been a really important feature, right? So that's essentially the amount by which the performance drops is the measure the permutation feature importance is going to assign to the importance of that feature. And you can do this, so you then do this for all your features, and again, you're just shuffling them one at a time. All the others are left intact. And at the end of the day, you have a set of feature importances. Now, what's really interesting about this approach and what distinguishes it from these isn't just the fact that it's not this weird bespoke, like highly specific, let's count the number of times this feature shows up in a decision tree, or like let's look at the biggest weight type thing. It's actually tied directly to the metric you care about. In theory, you can use permutation feature importance if you want to optimize for accuracy, or you want to optimize for precision, or you want to optimize for recall, whatever score you want to optimize for, you can use that for permutation feature importance. You can use that, see how that specific value is affected by shuffling different columns. The reason that's kind of interesting is you can imagine a situation where you're not interested in optimizing for accuracy. You really do just care much more about F1 score. And if that's the case in your problem, there might be some features that, whatever, they're really useful for accuracy, but they're not useful for F1 score. This is a bit of an edge case, but you can imagine that being the case, and this will allow you to catch that. This really allows you to optimize for the thing that is the most important to you in your particular problem setting. So that's permutation feature importance. The downside to it is you have to train a model for every shuffle that you could do, right? So you basically, you got to shuffle here, see how the model performs, shuffle here, see how it performs, and so on. And that takes time. So this is more time consuming than, perhaps certainly correlation coefficients or, other approaches that we've explored here, but it has a lot of advantages, right? It only depends, like at no point did I have to tell you what model I was using. I never started saying stuff like, oh, look at the structure of this decision tree, or look at the structure of this neural network, or this logistic regression. I didn't have to do that. I literally just said, take the data set, shuffle one of the columns, see what comes out, right? So this gets the benefit of a kind of model agnostic strategy while not being as oversimplistic as some of these approaches we saw earlier. It does manage to capture the things that your algorithm has learned about the data. So anyway, feature selection, permutation feature importance is something I highly recommend looking at. It has an implementation in scikit-learn, so fresh out of the box, you can just import it and start using it. I recommend checking it out. And anyway, I think that's all I have to say about it there. Any questions about permutation feature importance?
Yeah, this is cool. I learned about this first time. And as you said, for the large number of data, it must be difficult, right, to train multiple times. What do you suggest about like select features from, for example, the tree-based model, and then among them do it the permutation again? There will be limited feature,
yep.
And then do the
No, sorry, didn't mean to cut you off. Please continue.
Yeah, I was thinking that must be like, is that the good way of doing it, but or what do you suggest?
Yep. So as ever, I guess what I'm really presenting here are a bunch of different tools, and I think the fact that so many of you have jumped to sort of mixing and matching those tools and figuring out like how do they interact, that means you're really understanding this deeply. You're exactly right. You want to start doing stuff like that. So you do want to think about, okay, for my particular problem, yeah, just like too many columns at this stage. So let's not go straight for permutation feature importance or whatever else. Let's start with something really simple. I think Jeremy earlier, when we were talking about like why would you ever want to use correlation coefficients, I mentioned if you got a giant data set with huge number of columns, then yeah, go for it. But you probably don't want to just do all your feature selection that way. You probably want to go from 200 features down to maybe, I don't know, 40 or 30, and then maybe use permutation feature importance to kind of as a fine-tuning knob. And so that's the way to think about a lot of these things, right? We already know, for example, that we use techniques like variance threshold implicitly. Like, we don't often think about them even as feature selection. We actually sometimes refer to this as like data cleaning, right? And I think this illustrates that continuum. It's not like data cleaning ends or data engineering ends and feature selection begins. It's in fact, it's not even like model training ends or begins. Like even that's part of this process. The data science flow is this like very multi-headed hydra. It's all kind of mixed together. It's still useful to think of it as living in stages, but it's also helpful from time to time to kind of step back and realize, okay, I actually kind of did some feature selection already when I said I ditched the age column or ditched this other column that's missing a bunch of values. These things do qualify, and they can be mixed and matched in that way. So I definitely would say, yes, like the last thing you want is to look at your problem and have like shaky, nervous hands and be like, oh no, what if I try this and try that? And like my teacher said that I shouldn't mix these. Like just experiment and see what happens to that value that you're interested in. And if it goes up, hey, you're doing well, right? That's the way to think about it, I'd say.
Thank you.
Yeah, no problem. Yeah, Chris.
Yeah, just a quick question. Yeah, thanks. That's super interesting. And just kind of on that note, with sort of large sets of features and stuff, can you use the permutation feature importance with like groups of features? So say you scramble like 5 columns and then like test it and you'll see a drop, and then you can say you don't see a big drop, then you kind of know like, okay, none of those features are really important, but if you do another group of 5 and there's a big drop, then you can kind of like individually scramble each one, like kind of a divide and sort of conquer strategy.
Yep. So what you've just described is like I'm sure was a huge deal when it came out. Actually, this is a really good idea. In fact, it's in the scikit. I'm pretty sure it's in the scikit-learn implementation of permutation feature importance. So if you go and use it, I think you'll actually find, if not that, then there's a complementary package you can use to do this, where it's essentially just what you described. I mean, you say, okay, let's batch it. I don't want to go through all 200 of these one by one. Let's take, these 5, shuffle them, and so on. So yeah, you're absolutely right. There are variants on this that do get implemented.
Nice. Okay. Thanks. Super interesting.
Yeah, no problem. And these are, so I think there's something, this would happen to me in physics often. I would like come up with something, a thought, and then, you'd learn, somebody else has already thought of it. But those ideas would be minor revolutions if it just happened to be the first time that people thought of them. So these are really great suggestions. I mean, yeah, anyway, thanks for sharing that. Any other questions before we put a bow in it? Okay. All right. Well, so I recorded this. It'll be live. I have to apologize again for the kerfuffle on the scheduling of this. We'll be back on a regularly scheduled Monday at 3:30 p.m. EST as of next week and on. And I'll post to see if there's interest in another office hour session on the same topic later this week, just for people who missed it. So feel free to attend that if it turns out there's enough interest for it. Awesome. All right. Well, have a great rest of the day, everybody.
Thank you.
Thank you. Cheers. Bye, everybody.
Yeah, this is awesome. Yeah.
Thanks,
Bye.
Kieran. Bye-bye.